June 23, 1944. Mid-Atlantic Ocean, 850 nautical miles west of the Cape Verde Islands. A 500-pound depth bomb punched through the black water and detonated against the steel hull of the Japanese submarine I-52, ripping open her pressure hull like a tin can crushed under a boot. The explosion sent a column of white water 30 feet into the night sky. Inside, 94 men felt the ocean rush in through the wound, flooding compartments in seconds, collapsing bulkheads like paper walls. The submarine's back broke at 200 feet, and as she spiraled toward the bottom of the Atlantic, her dying screams were recorded by tiny floating cylinders, bobbing on the surface above. Devices no bigger than a milk bottle. Devices that had heard every single turn of her propeller screws from 20 miles away. And the men who killed her. They never saw her. Not once. They listened to her die through headphones sitting in the belly of a torpedo bomber circling in total darkness, guided by nothing but sound. This is the story of how a $65 gadget built by American factory workers who never fired a gun destroyed the most feared weapon in the Atlantic. This is the story of the Sonobuoy. And it begins not with admirals or generals, but with a 37-year-old radio technician from Camden, New Jersey, named Harold Vance. A man who had never been to sea, who had never heard a torpedo explode, who had never watched a ship sink, but whose invention would send over 150 German U-boats to the bottom of the ocean and change submarine warfare forever. But before we get to Harold, we need to understand just how badly the Allies were losing. 1940 to 1942. The darkest years of the Atlantic War. And the numbers were staggering. In 1940, German U-boats sank 471 Allied merchant ships. In 1941, that number climbed to 496. By the spring of 1942, after America entered the war, and Admiral Karl Donitz unleashed his wolf packs against virtually unprotected American coastal shipping, the slaughter reached industrial proportions. In June 1942, alone, U-boats destroyed 144 ships, totaling over 700,000 tons of cargo. Food, fuel, weapons, tanks, aircraft, medicine, everything the Allies needed to fight the war was being sent to the bottom of the Atlantic by submarines that were invisible once they slipped beneath the waves. The problem was brutally simple. The ocean is dark. Sound travels strangely underwater, and a submarine running silent at 50 meters depth might as well have been on the moon for all the Allied navies could do about it. Surface ships carried ASDIC, an early form of active sonar that sent out pinging sound waves and listened for echoes bouncing off submarine hulls. But ASDIC had crippling limitations. Maximum reliable detection range was roughly 3,000 yards, less than 2 miles. It only worked well when the hunting ship was moving slowly, which made the hunter vulnerable. And submarines could hear the pinging from much farther away than the ping could detect them, meaning the hunted always knew the hunter was coming. Aircraft were faster, could cover more ocean, but had their own fatal weakness. They could spot a surface submarine from miles away, but the moment that submarine dove, it vanished. Gone. Invisible. Aircraft had no sonar, no way to peer beneath the waves. A pilot could circle over the exact spot where a U-boat had crashed, dived, and see absolutely nothing. The submarine would simply wait at depth, running on electric motors, making almost no noise, until the aircraft ran low on fuel and left. Then the submarine would surface and resume killing. Between January and August 1942, the Allies tried everything. More escort ships, bigger convoys, better radar for aircraft, new camouflage patterns, longer-range patrol bombers. Nothing worked well enough. The U-boats kept coming. Kept sinking, kept killing. British children went hungry because cargo ships carrying food were burning in the mid-Atlantic. Soldiers drowned because troop transports were torpedoed before reaching Europe. Winston Churchill himself would later admit that the U-boat threat was the only thing during the entire war that truly frightened him. The Allied High Command was desperate, and desperation, as it turned out, was exactly the environment where a crazy idea could finally get a hearing. But everything was about to change because of one man nobody was paying attention to. Harold Vance was not a soldier. He was not an engineer with prestigious degrees. He was a radio technician at RCA's manufacturing plant in Camden, New Jersey, a quiet man with thick glasses and oil-stained hands, who spent his days testing vacuum tubes and calibrating radio receivers on an assembly line. He had no military background, no connections in Washington, no reputation in scientific circles. What he had was an obsession with underwater sound. Before the war, Vance had spent years as an amateur radio enthusiast, building his own receivers in his garage, picking up signals from the ships at sea, from weather stations, from shortwave broadcasters around the world. He understood radio waves the way a musician understands melody, intuitively, instinctively. And he understood something else too. He understood that sound in water behaved differently than sound in air. Water was denser, and sound traveled through it faster, farther, and more faithfully than through the atmosphere. In May 1941, when Professor PMS Blackett of the British Admiralty's Committee for Anti-Submarine Measures floated the idea of expendable sonar devices dropped from aircraft, British naval engineers immediately declared it impractical. Too many technical problems. The devices would need to be small enough to carry in quantity, rugged enough to survive impact with the ocean, waterproof enough to function in salt water, equipped with both a hydrophone to listen underwater and a radio transmitter to broadcast what it heard, powered by batteries lasting hours, and cheap enough to throw away after a single use. Interesting in theory, one British engineer wrote in his assessment, but the technical challenges are insurmountable within any reasonable time frame. When that assessment crossed the Atlantic and landed on the desk of the Office of Scientific Research and Development in Washington, it eventually filtered down to RCA's Defense Contracts Division in Camden. Harold Vance read it during his lunch break, and something clicked in his mind. He didn't see insurmountable problems. He saw a radio receiver hanging from a float. He had been building those his entire life. That night in his garage workshop, Vance sketched the first rough design of what would become the CRT-1 Sonobuoy, a waterproof canister containing a simple radio transmitter, a battery pack, and a wire running down to a hydrophone that would hang 30 feet below the surface. The whole thing would be activated by a switch connected to a parachute. Drop it from an aircraft. The parachute deploys, pulls the activation switch. The canister hits the water. The hydrophone sinks to listening depth, and the transmitter starts broadcasting whatever it hears on a preset radio frequency back to the aircraft above. Simple, crude, absolutely insane by the standards of precision-obsessed naval engineers who believed anti-submarine equipment needed to be sophisticated, complex, and operated by trained specialists. Vance's supervisor at RCA, a man named Thomas Mitchell, looked at the sketch and frowned. "Harold, this thing looks like you built it from spare parts in your kitchen." "That's the point," Vance replied. "It needs to be cheap enough to throw away. We don't recover them. We make thousands and drop them everywhere." Mitchell shook his head. "The Navy will never buy a disposable sonar system. They want something reusable, something precision engineered." Vance pushed back. By the time they finish precision engineering, it will have lost the Atlantic. He was right. And someone in Washington agreed. In June 1941, 6 months before Pearl Harbor, RCA received a classified contract to develop Vance's concept. The budget was modest. The expectations were low. Most naval officers who reviewed the project considered it a sideshow, a curiosity that might produce interesting data, but would never replace proper shipboard sonar. They didn't understand that Vance wasn't trying to replace anything. He was trying to create something entirely new. A weapon system where the individual components were worthless, but the network they created was devastating. By March 1942, 3 months after Pearl Harbor turned the theoretical war into a desperate one, a working prototype existed. It was ugly. It was crude. A German engineer would have been embarrassed by it. The soldering was rough. The waterproofing was industrial sealant, slathered on by hand. The hydrophone was a modified commercial unit, and the radio transmitter had a range of only 15 miles. But it worked. March 7th, 1942. Water south of New London, Connecticut. Navy blimp K-5 drifted over the gray Atlantic carrying 6 prototype Sonobuoys in its bomb bay. Below the surface, the American submarine S-20 ran submerged at 4 knots, completely silent following standard evasion procedures. She was the test target, and her crew had been told to make themselves as hard to find as possible. The blimp dropped 3 buoys in a triangle pattern, each splashing into the water and beginning to transmit on different frequencies. The radio operator aboard K-5, Petty Officer James Sullivan, pressed his headphones tight against his ears and listened.
For 2 minutes, nothing but ocean noise, waves, distant ship traffic, the random clicks and groans of the deep. Then Sullivan heard it, a faint rhythmic beating, soft as a heartbeat through a wall, the unmistakable sound of propeller blades turning through water. Contact. He reported, his voice barely steady. Bearing approximately 190. Definite submarine propeller noise. Detection range 3 nautical miles. 3 miles. A submarine commander could be running silent, following every procedure in every doctrine manual ever written, making almost no sound at all. And an aircraft overhead could hear him from 3 miles away. Not see him, not detect him with radar, actually hear him. Listening to the faint rhythm of his propellers through a $65 device floating on the surface. The implications were staggering.
But this was only the beginning. RCA shifted to mass production immediately. By June 1942, the AN/CRT-1 Sonobuoy was rolling off assembly lines. By August, American aircraft were dropping them operationally in the Atlantic. The buoys had 6 available radio frequencies, allowing a single aircraft to deploy multiple units and listen to each one separately, creating a detection grid across miles of ocean. They could operate continuously for 6 hours. They cost $65 each. $65 to strip away a submarine's invisibility, and the results were immediate. In August 1942, Kapitänleutnant Werner Hartmann, commanding U-254 in the North Atlantic, became one of the first U-boat commanders to encounter Sonobuoys operationally. He was submerged at 50 meters, running silent following textbook procedures, when small objects began splashing into the water above him. Not depth charges, something lighter, something that floated and transmitted strange radio signals on multiple frequencies. For 6 hours, an American aircraft tracked his every movement with terrifying precision, dropping depth charges that walked closer and closer to his position, despite the submarine being completely invisible beneath 50 meters of gray Atlantic water. Hartmann survived by draining his batteries in a desperate full-speed run east. He immediately reported to U-boat command in Paris. His message was blunt: attacked by aircraft using unknown detection method. Submarine tracked continuously for 6 hours while submerged and running silent. Conventional explanation? Impossible. Admiral Donitz's headquarters dismissed the report. Aircraft probably used visual sighting before the dive. Depth charge patterns were random. BDU has no intelligence indicating new Allied detection capabilities. They were wrong. Catastrophically wrong. And their refusal to understand what was happening would cost hundreds of submarines and thousands of lives. Because Harold Vance's crude little device, that $65 canister that looked like it was built from spare parts in a kitchen, was just getting started. The Americans weren't building a weapon. They were building a system, a surveillance network that would blanket the entire Atlantic Ocean with invisible ears turning every square mile of water into a listening post, transforming the submarine's greatest advantage into its greatest vulnerability. The ocean itself was about to become the enemy. And in Part 2, we will see what happened when the full network went operational, when hundreds of aircraft began dropping Sonobuoys by the thousands, when German U-boat commanders realized that silence was no longer safety, and when the most dramatic kill of the entire war, the hunt for the gold-carrying Japanese submarine, I-52, proved that nowhere in the Atlantic, not even 20 miles from the nearest listener, was safe anymore. The age of submarine invisibility was over. Most U-boat commanders just didn't know it yet. In Part 1, a radio technician named Harold Vance built a $65 listening device in his garage that could hear submarines from 3 miles away. The Navy tested it. It worked. Mass production began. And in August 1942, the first sonobuoys started falling into the Atlantic Ocean. But convincing a handful of engineers in a New Jersey laboratory was one thing. Convincing the United States Navy, the most tradition-bound military institution in the Western Hemisphere, to bet the entire Battle of the Atlantic on a disposable gadget that looked like a tin can with a wire hanging out of it, that was a wayar all by itself. And here is where everything got worse. Because in September 1942, while U-boats were sinking an average of 4 Allied ships every single day, while 30,000 merchant sailors had already died in the freezing Atlantic while Britain was running dangerously low on food and fuel, the Sonobuoy program slammed headfirst into Rear Admiral Wilson R. Caldwell, Director of Naval Ordnance Testing, a man who had spent 31 years in the Navy and who believed with the unshakable conviction of a career bureaucrat that expendable weapons were a waste of taxpayer money. Caldwell was not a fool. He was worse. He was competent, respected, and wrong. He had overseen torpedo development, depth charge improvements, and mine warfare programs. He understood anti-submarine warfare from the surface ship perspective, and in his experience, every detection system worth deploying was a precision instrument operated by trained specialists aboard warships. The idea of throwing away sonar devices like used cigarettes offended everything he believed about naval warfare. September 14th, 1942. Bureau of Ordnance Conference Room, Maine. Navy Building, Washington, D.C. Harold Vance stood at one end of a long mahogany table, his prototype Sonobuoy sitting on the polished wood like a beer can at a formal dinner. Across from him sat Caldwell, flanked by 6 naval officers, none of whom had ever heard of the CRT-1 program, and all of whom looked at Vance the way surgeons look at a plumber offering medical advice. Vance began his presentation. He explained the concept: the hydrophone, the radio transmitter, the parachute activation system, the 6 available frequencies, the 3-mile detection range confirmed in testing, the $65 unit cost. He showed the data from the K-5 blimp test. He showed production estimates from RCA. He showed deployment projections suggesting that a single aircraft carrying 20 buoys could create a surveillance network covering 60 square miles of ocean. Caldwell listened without expression. When Vance finished, the Admiral leaned forward and spoke. Mr. Vance, you are asking the United States Navy to spend millions of dollars manufacturing devices that we will deliberately throw into the ocean and never recover. Devices with a 6-hour battery life. Devices that cannot be reused, cannot be maintained, cannot be calibrated in the field. You are asking us to treat sophisticated electronic equipment like ammunition. That is exactly what I am asking, sir. Caldwell's jaw tightened. And what happens when the enemy recovers one of these devices? They will know our frequencies. They will develop countermeasures. They will render your entire program obsolete overnight. Then we change the frequencies, sir. We build the next batch on different channels. They cost $65. We can afford to stay ahead. The room went silent. A civilian had just told a rear admiral that his objection was irrelevant. Caldwell's face darkened. He stood, gathered his papers, and delivered his verdict. This program will not receive Bureau of Ordnance endorsement. The detection range is insufficient for fleet operations. The unit reliability is unacceptable by Navy standards. And the expendable concept contradicts fundamental principles of responsible material management. I recommend redirecting these funds toward improving shipboard ASDIC systems, which have proven combat effectiveness. This meeting is over. Vance walked out of the main Navy building into the September heat, carrying his prototype in a canvas bag, knowing that the man who controlled weapons testing for the entire Navy had just killed his program. Without Bureau of Ordnance endorsement, no operational commander would deploy Sonobuoys. Without deployment, there would be no combat data. Without combat data, there would be no proof that the system worked. Without proof, there would be no funding. The program would die in a filing cabinet while U-boats continued slaughtering merchant ships at a rate of 120 per month. That night, Vance sat in his hotel room and wrote a letter. Not to Caldwell, not to the Bureau of Ordnance. He wrote to a man he had never met, a man whose name he had seen in a technical journal 6 months earlier, Commander William S. Parsons, a naval officer assigned to the Office of Scientific Research and Development, known among scientists as one of the few military men in Washington who actually understood physics. But Vance had found an unexpected ally, and that ally was about to change everything. Commander Parsons read Vance's letter on September 19th. By September 22nd, he had requested all test data from the K-5 trials. By September 25th, he had arranged a private meeting with Dr. Vannevar Bush, the director of OSRD, and one of the most powerful scientific administrators in the country. Bush reported directly to President Roosevelt. He had the authority to bypass the Bureau of Ordnance entirely. Parsons understood something Caldwell did not. The Atlantic War was not a naval engagement in the traditional sense. It was an industrial problem. Germany was producing U-boats faster than the Allies were sinking them. The Allies needed a detection system that could scale at industrial speed, and that meant expendable, mass-produced good enough technology deployed in overwhelming quantity. Precision was a luxury the Atlantic could not afford. Bush agreed, but he imposed one condition. There would be a formal demonstration before senior naval leadership, not in sheltered coastal waters, not against a cooperative test submarine, in open ocean conditions against a submarine actively trying to evade detection with skeptical admirals watching from a command ship. One chance. If the Sonobuoys failed under realistic combat conditions, Caldwell would be vindicated, and the program would be terminated permanently. The demonstration was scheduled for October 12, 1942. Vance had 17 days to prepare. He needed 50 working Sonobuoys. RCA's production line had manufactured only 31 units total, and of those 8 had failed waterproofing tests. Vance pulled technicians from 3 other projects, ran the assembly line 18 hours a day, hand-tested every unit personally, and by October 10th had 53 functional buoys packed in wooden crates and loaded onto a Navy transport truck bound for Norfolk, Virginia. He also needed an aircraft crew trained in Sonobuoy deployment and monitoring. The Navy assigned Lieutenant James McAllister, a patrol bomber pilot who had never heard of Sonobuoys, and gave Vance exactly 48 hours to train him. They practiced over a swimming pool at the Norfolk Naval Air Station, dropping weighted dummy buoys from a scaffolding platform, while Vance explained frequency switching, signal interpretation, and triangulation techniques. It was absurd. It was desperate. It was all they had. October 12, 1942. Atlantic waters off Norfolk, Virginia. Weather conditions moderate seas. Overcast skies wind 15 knots from the northwest. The destroyer USS Cleves served as the observation platform, carrying Rear Admiral Caldwell, Commander Parsons Dr. Bush's representative, and 11 other senior officers. Somewhere beneath the gray water, the submarine USS Mackerel ran submerged at 60 feet. Her captain, under orders to employ full evasion procedures and avoid detection by any means necessary. McAllister's PBY Catalina took off at 0800 hours. In the aircraft's belly, Vance crouched beside the radio receiver wearing headphones and monitoring 6 frequencies simultaneously. His hands were shaking. His mouth was dry. 17 days of preparation, 53 Sonobuoys, the entire future of underwater acoustic surveillance, riding on whether his garage-built invention could find a submarine that was trying very hard not to be found. At 0830, McAllister dropped the first pattern. 5 buoys splashing into the Atlantic in a cross formation, each transmitting on a different frequency. Vance switched between channels. Static, ocean noise, the hiss and rumble of waves, wind interference, nothing that sounded like a submarine. 8 minutes passed. On the Cleves, Caldwell checked his watch. At 0838, Vance heard something on Channel 3, a faint rhythmic pulse. He pressed the headphones harder against his ears, adjusting the receiver's gain. The pulse became clearer. A low, repetitive beating, steady as a metronome. Propeller noise, definitely mechanical, definitely underwater. Contact, he told McAllister through the intercom. Channel 3, bearing approximately 210 relative to buoy 3. McAllister banked the Catalina and dropped 3 more buoys in a triangle around the estimated bearing. Within 4 minutes, Vance had the submarine on 3 different channels, each giving a different signal strength. By comparing the relative loudness on each buoy, he calculated a bearing, a rough speed estimate, and a direction of travel. He's heading northwest at approximately 5 knots depth, probably 60 to 80 feet, based on sound characteristics. Signal is clear on channels 3, 5, and 6. McAllister radioed the Gleaves with the submarine's estimated position. The destroyer dispatched its own ASDIC-equipped escort to verify. 22 minutes later, the escort confirmed contact with USS Mackerel at almost exactly the position Vance had reported. The margin of error was less than 400 yards. On the Gleaves, the officers exchanged glances. Caldwell's expression had not changed, but Vance was not finished. Over the next 3 hours, the Sonobuoy network tracked Mackerel continuously as the submarine executed every evasion technique in the book. Course changes, speed changes, depth changes, silent running, even a complete engine shutdown, drifting on battery power alone. The buoys heard everything. Every course change produced a shift in propeller bearing across multiple buoys. Every speed change altered the sound intensity. When Mackerel tried to hide behind a thermocline layer, 2 of the buoys lost contact, but the third, positioned directly above the thermal boundary, maintained a faint but trackable signal. When the submarine shut down her engines entirely, the buoys picked up the residual sound of water flowing over the stationary hull popping noises from pressure changes, and the faint hum of auxiliary equipment still running inside the boat. At 11:45 hours, Vance reported his final tracking data. USS Mackerel, bearing 175 range, approximately 2 miles from buoy pattern center depth, estimated 90 feet speed, 3 knots heading south-southeast. Current track maintained for 47 consecutive minutes without signal loss. The escort verified again. Position accurate within 300 yards. The Sonobuoys had tracked a submarine executing active evasion maneuvers for over 3 hours from an aircraft flying at altitude, using technology that cost less than a good pair of binoculars. The observation report, written by Commander Parsons and co-signed by 3 of the 11 senior officers aboard Gleaves, reached Dr. Bush's desk the following morning. Its conclusion was one sentence. The CRT-1 Sonobuoy system demonstrated reliable detection and continuous tracking of a submerged evading submarine under realistic ocean conditions and should be approved for immediate operational deployment. Caldwell did not co-sign, but he did not file a formal objection either. The data was undeniable. Within 2 weeks, the Navy authorized an initial production order of 10,000 Sonobuoys. Within 2 months, that order expanded to 50,000. By the end of 1942, RCA had delivered 18,000 units and was expanding production capacity to meet a projected demand of 150,000 units by the end of 1943. The cost per unit dropped from $65 to $48 as manufacturing efficiencies improved. But building the buoys was the easy part. Getting aircrews to use them was something else entirely. Patrol squadrons across the Atlantic had been fighting U-boats for over a year using radar, visual search, and gut instinct. Their pilots were experienced, aggressive, and deeply skeptical of any technology that required them to fly in circles, listening to radio static instead of hunting with their eyes. Sonobuoys seemed passive, indirect, the opposite of everything a combat pilot valued. Vance spent November and December 1942 traveling between Atlantic patrol bases from Newfoundland to Iceland to the Azores, personally training aircrews in Sonobuoy deployment and interpretation. He carried his equipment in duffel bags. He slept on cots in aircraft hangars. He demonstrated the system to pilots who openly mocked the idea of listening for submarines through what one flight officer called fancy fishing bobbers. The breakthrough came not from Vance's training sessions, but from combat. On January 8, 1943, a VP-84 patrol bomber operating south of Iceland dropped a Sonobuoy pattern on a suspected U-boat contact. The buoys detected a submarine running at 70 meters depth, completely invisible to radar and visual search. The aircraft vectored in, dropped a pattern of depth charges guided entirely by Sonobuoy bearings, and forced the U-boat to surface with heavy damage. The submarine was U-337. It was captured intact, its crew taken prisoner. It was the first confirmed Sonobuoy-assisted kill in the Atlantic War. Word spread through the patrol squadrons faster than any official memo could travel. Within weeks, every Atlantic patrol crew
Wanted Sonobuoys. Demand exceeded supply by March 1943.
By June, every long-range patrol aircraft in the Atlantic carried a minimum load of 15 buoys per sortie. And the Germans? The Germans had no idea what was happening. In 1942, U-boats had sunk 160 Allied ships. In the first 6 months of 1943, as Sonobuoy deployment expanded across the Atlantic, that number began falling. Not gradually, dramatically. Monthly sinkings dropped from an average of 97 ships in late 1942 to 34 ships by May 1943. In the same period, U-boat losses tripled. In May 1943 alone, 41 U-boats were destroyed, so many that Admiral Donitz temporarily withdrew all wolf packs from the North Atlantic, an event the Allies called Black May. The German submarine force was bleeding, and they could not understand why. U-boat commanders reported being attacked by aircraft that had no business knowing where they were. They reported mysterious splashing sounds, strange radio transmissions from the surface, depth charge patterns of impossible accuracy against submarines running deep and silent. Admiral Donitz demanded answers from his intelligence staff. His technical experts insisted that radio waves could not penetrate seawater. Therefore, the submarine reports must be exaggerations or errors. The commanders were mistaken. The attacks were coincidental. There was no new Allied detection technology. They were catastrophically wrong. And now, in the summer of 1943, the secret was about to get bigger. Because the Americans were not just using sonobuoys to hunt individual submarines anymore. They were building something far more ambitious. Permanent underwater surveillance barriers stretching hundreds of miles across the Atlantic, capable of detecting every submarine that tried to cross them. Networks so vast that no U-boat could reach the convoy lanes without being heard tracked and marked for destruction. The Sonobuoy had proven it could find submarines. Now the question was whether it could win a war. But as the surveillance network expanded, a new threat emerged. In September 1943, a German patrol boat operating in the Bay of Biscay recovered a sonobuoy that had washed ashore on the French coast. The device was shipped to Berlin. German naval intelligence began examining it. And, for the first time, the Kriegsmarine understood exactly what they were fighting against. The race between detection and evasion between ears, and silence between American industrial output and German engineering genius was about to explode. And the real war was only just beginning. A radio technician from New Jersey built a $65 listening device that could hear submarines underwater. The Navy laughed at it. Then they tested it. Then they mass-produced 150,000 of them. And by the summer of 1943, sonobuoys were falling into the Atlantic like rain, turning the ocean into a surveillance network that stretched from Newfoundland to the Azores, from Iceland to the Bay of Biscay. U-boat losses tripled. Monthly Allied ship sinkings dropped from 97 to 34. Admiral Donitz pulled his wolf packs out of the North Atlantic in what the Allies called Black May. The tide of the Atlantic War had turned. But then, in September 1943, a German patrol boat found a sonobuoy washed up on the French coast. Berlin's engineers cracked it open. And for the first time, the Kriegsmarine understood exactly what was killing their submarines. This was no longer a secret weapon. This was an arms race. And the stakes had never been higher. September 28, 1943, German Naval Intelligence Headquarters, Berlin. Korvettenkapitän Ernst Kupfer stood before a disassembled sonobuoy laid out on a laboratory table like a dissected animal. The components were embarrassingly simple. A waterproof canister, a battery pack, a radio transmitter operating on one of 6 preset frequencies, a wire leading to a hydrophone designed to hang approximately 30 feet below the surface. Total parts count fewer than 40 individual components. Estimated manufacturing time per unit less than 90 minutes. Kupfer's report to Admiral Donitz was blunt. The Americans have industrialized submarine detection. Each device cost them approximately $50. They are deploying them by the thousands. A single aircraft can carry 20 units and create a surveillance network covering 60 square miles of ocean in minutes. Our submarines are being detected not by skill or superior technology, but by quantity. The Americans have turned the Atlantic into a listening room. Donitz convened an emergency meeting of his technical staff. The discussion lasted 7 hours. German engineers proposed 3 countermeasures. First, acoustic decoys devices that could be ejected from torpedo tubes to create false propeller signatures and confuse the Sonobuoy network. Second, hull coatings rubber-based materials applied to the submarine's exterior to absorb sound rather than reflect it, reducing the acoustic signature. Third, the Pillenwerfer, an effervescent chemical tablet that created a cloud of bubbles to scatter and absorb sonar signals. Development began immediately, but German engineering culture demanded perfection. The acoustic decoy program, codenamed Bold, required 18 months of testing before naval ordnance would approve production. The hull coating program consumed rare rubber supplies that were already desperately needed for other war production. The Pillenwerfer worked in trials but proved unreliable in the cold, deep waters of the North Atlantic, where temperature and pressure degraded the chemical reaction. Meanwhile, the Americans simply kept building more Sonobuoys. 50,000 in 1943. 100,000 projected for 1944. The Germans were trying to engineer their way out of a problem that was fundamentally about industrial output. And they were losing the race before it even started. By December 1943, U-boat losses had reached catastrophic levels. Donitz was losing submarines faster than German shipyards could build them. In the last quarter of 1943, 67 U-boats were destroyed, the majority by aircraft using Sonobuoy-assisted detection. Crew survival rates plummeted. Experienced commanders were dying faster than new ones could be trained. The average life expectancy of a U-boat crew member had dropped from 18 months in 1941 to less than 6 months. But the Sonobuoy program was not without its own crisis. In November 1943, a series of operational failures nearly derailed the entire system. Patrol squadrons in the North Atlantic reported that Sonobuoys, dropped in water temperatures below 40 degrees Fahrenheit, were failing at alarming rates. The batteries designed for temperate conditions lost up to 60% of their capacity in near-freezing water. Hydrophones cracked from thermal shock. Radio transmitters shorted out when condensation formed inside the canisters during rapid temperature changes between the warm aircraft cabin and the frigid ocean surface. In a single week, VP-63 Squadron, operating south of Iceland, reported that 23 out of 41 deployed buoys failed within the first hour, a failure rate of 56%. Patrol reports flooded back to Washington. Commanders who had grown to rely on Sonobuoys suddenly found themselves deaf again, circling over empty ocean with useless equipment bobbing in the waves below. The criticism was immediate and fierce. Rear Admiral Caldwell, who had opposed the program from the beginning, sent a memorandum to the Chief of Naval Operations, arguing that the Sonobuoy program had been rushed into production without adequate testing, and that funds should be redirected to proven shipboard sonar systems. Several squadron commanders echoed his concerns. The expendable concept, they argued, had led to sloppy manufacturing because no one cared about quality when the product was designed to be thrown away. Harold Vance flew to Reykjavik in December 1943 into the teeth of an Icelandic winter to diagnose the problem firsthand. What he found was not a design flaw, but a manufacturing shortcut. To meet the enormous production demands, RCA's subcontractors had switched from military-grade battery cells to cheaper commercial equivalents that could not withstand extreme cold. The waterproofing sealant had been thinned to speed application on the assembly line. Quality control inspections had been reduced from 100% testing to random sampling. Vance spent 3 weeks at RCA's Camden facility, personally overseeing a redesign of the cold weather package. New lithium-based batteries replaced the commercial cells. A thicker silicone sealant replaced the thinned compound. Every unit was individually pressure tested before shipment. By January 1944, The failure rate had dropped from 56% back to under 8%. The crisis was over. But it had consumed precious weeks during which U-boats operated with reduced surveillance pressure. And then came the hunt that changed everything. March 10th, 1944. The Japanese submarine Y-52 departed Kure Naval Base on her maiden voyage. She was enormous, 356 feet long, displacing two 564 tons, with a crew of 94. Her cargo holds carried a fortune: 11 tons of tungsten, 10 tons of molybdenum, 3 tons of opium, 54 kilograms of pure caffeine, and most importantly, 146 gold bars weighing 2.2 tons. Payment for German optical and radar technology. Her mission was to cross 15,000 nautical miles of hostile ocean from Japan to German-occupied France through waters patrolled by Allied aircraft surface ships and submarines. Commander Uno Kamio was told the voyage was dangerous, but feasible. He was told that Japanese naval codes were secure. He was told that submarines operating in the deep Atlantic were nearly impossible to track. He was told, oh, wrong. American codebreakers had been reading Japanese naval communications for months. They tracked I-52 from the moment she left port. They monitored her stop in Singapore, where she loaded 120 tons of tin, 60 tons of rubber, and 3 tons of quinine. They intercepted every position report she transmitted, and they knew about her scheduled rendezvous with German U-boat U-530 on June 22nd at coordinates 15 degrees north, 40 degrees west, where she would receive radar detection equipment and 2 German technicians. The escort carrier USS Bogue and her task force of 5 destroyer escorts were vectored to the rendezvous point. Captain Aurelius Vossler commanded the group. His air wing included 9 Wildcat fighters and 12 Avenger torpedo bombers. This team had already sunk 13 enemy submarines. They were the most experienced hunter-killer group in the Atlantic, June 23, 1944. Night falls over the mid-Atlantic. U-530 surfaces. I-52 approaches. The 2 submarines meet in the darkness, exchange personnel and equipment, and separate. U-530 heads for Trinidad. I-52 continues toward Europe. Her diesels churning at 15 knots, her new German radar equipment still packed in crates below deck. At 23:40 hours, Lieutenant Commander Jesse Taylor's Avenger picks up I-52 on radar. 12 miles. The submarine has no idea she is being watched. Taylor approaches, drops flares. The ocean lights up white. I-52 crash dives. 90 seconds, and she is gone. Under the waves. Invisible. Safe. Except she is not safe. Not anymore. Taylor's crew begins dropping sonobuoys. Purple, orange, blue, red. Each buoy transmits on a different frequency. Each one listens. Taylor's radio operator switches between channels, and within minutes, I-52's propeller noise is coming through on 3 separate buoys. Clear, distinct, unmistakable. The submarine is heading south at 8 knots, depth increasing. She thinks she has escaped. Taylor calculates a position. Drops 2 Mark 54 depth bombs. The first explodes over I-52's starboard side. Close. A column of water shoots 30 feet into the air, but not close enough to kill. I-52 goes deeper, turns hard to port. Commander Uno is evading. Standard procedure. Every submarine commander knows these maneuvers. But the Sonobuoys hear everything. Every turn, every change in speed, every shift in depth. The submarine is broadcasting her own position through the simple act of moving through water. At 23:52 hours, Taylor drops a Mark 24 acoustic homing torpedo. Codename Fido. The weapon enters the water. Its acoustic sensors activate. It listens for the loudest sound in the ocean. In the empty mid-Atlantic far from shipping lanes, the loudest sound is I-52's propellers. Fido turns toward the submarine, silent. No wake, no warning. The explosion is captured on Taylor's Sonobuoys. A sharp crack. Then the sound of a pressure hull collapsing. Metal screaming. Compartments flooding. Bulkheads buckling inward under the crushing weight of the Atlantic. 94 men. 146 gold bars. 2.2 tons of precious metal. All of it spiraling down to the ocean floor 3 miles below. The recording exists today in the National Archives. The last I-52 heard through $65 devices floating on the surface. But the night was not over. Lieutenant William Gordon arrived on station after midnight with civilian acoustic expert Price Fish aboard his aircraft. The Sonobuoys were still transmitting, and Fish heard something that stunned everyone. Faint propeller noise. Another submarine, still running. It was U-530, the German boat that had delivered the equipment hours earlier. She was 20 miles away. 20 miles. And the Sonobuoys could hear her clearly through a phenomenon called a surface duct, a temperature layer near the surface that channeled sound across extraordinary distances. 20 miles of detection range. From a device that cost $65, dropped from an aircraft, listening through miles of ocean, as if the water itself had become a microphone. The I-52 kill sent shockwaves through Allied command. Not because of the gold, though, that made headlines later. Because the Sonobuoy network had demonstrated capabilities that exceeded every prediction. Detection at ranges previously thought impossible, continuous tracking of an evading submarine in total darkness. Successful prosecution using acoustic homing torpedoes, guided entirely by Sonobuoy data. And the incidental detection of a second submarine, 20 miles away, a submarine that had no idea it was being heard. The numbers told the rest of the story. In 1942, before widespread Sonobuoy deployment, it took an average of 87 aircraft attacks to sink one submarine. By mid-1944, that ratio had improved to 16-1. Monthly Allied ship losses had dropped from an average of 97 in late 1942 to fewer than 20 by the summer of 1944. U-boat operational patrols, which had averaged 60 active boats at any given time in 1942, dropped to fewer than 30 by mid-1944 because submarines were being sunk faster than Germany could replace them. The psychological damage was even more devastating than the physical losses. Captured U-boat crews consistently described the Sonobuoys as the most terrifying weapon they faced. Not because they killed directly, depth charges and torpedoes did that, but because they destroyed the one thing every submarine depended on. Invisibility. Kapitänleutnant Georg Schneider, captured after his boat was sunk off Halifax, told British interrogators something that appeared in intelligence summaries within days. "We cannot hide anymore. The ocean used to protect us. Now it betrays us. Every sound we make they hear. How do you fight an enemy who can hear through miles of water? Morale across the U-boat fleet collapsed." Submarine duty, once considered elite service in the Kriegsmarine, became a death sentence that men desperately tried to avoid. Commanders reported crewmen injuring themselves to avoid patrols. Experienced officers requested transfers to surface ships. The average age of U-boat commanders dropped as veterans were killed faster than they could be replaced, leaving younger, less experienced officers in command of boats entering an ocean that had turned against them. Admiral Donitz pinned his remaining hopes on the Type Wind submarine, a revolutionary design with high underwater speed and massive battery capacity that might outrun Sonobuoy detection. But the Type Nuam arrived too late. Only 2 completed combat patrols before the war ended. The Sonobuoys had won the race. By May 1945, when Germany surrendered, Sonobuoys had contributed to the sinking or forced surfacing of over 150 U-boats. They had rendered hundreds more patrols ineffective by detecting and driving submarines away from convoy routes. The total cost of the entire Sonobuoy program was approximately $9.75 million for 150 000 units deployed during the war. Less than the cost of a single aircraft carrier. Less than the cost of the cargo lost in a single bad month of 1942. Harold Vance received no medal. His name appeared in no newspaper. The Sonobuoy program remained classified until well after the war ended. The man who had built the prototype in his garage, who had fought the Navy bureaucracy, who had personally trained air crews from Iceland to the Azores, returned to his workbench at RCA's Camden plant and went back to testing vacuum tubes. But there is one more chapter to this story, a chapter about what happened after the war, about the Cold War submarine arms race that made the Sonobuoy not just a weapon, but the foundation of an entire global surveillance system. About the Soviet Union's desperate attempts to build submarines quiet enough to evade the technology. About Harold Vance's final years and the letter he received in 1962 that made him sit down at his kitchen table and cry. That chapter is next, and it is the one almost nobody knows. A radio technician from Camden, New Jersey sketched a device on his kitchen table that cost $65 to build. The Navy called it impractical. A rear admiral tried to kill the program. A freezing winter in Iceland nearly broke it. But by the summer of 1944, that device, the Sonobuoy, had turned the Atlantic Ocean into the largest surveillance network in human history. Over 150 000 units deployed. Over 150 U-boats sunk or forced to surface. Monthly Allied shipping losses cut by 80%. The Battle of the Atlantic, the longest continuous campaign of the entire Second World War, decided in large part by a gadget no bigger than a milk bottle. But what happened to the man who started it all? What happened to Harold Vance when the guns went silent and the world moved on? This story has one final twist, and it is the one almost nobody expected. Because sometimes the people who change history the most are the ones history forgets the fastest. May 8, 1945. V-Day. The war in Europe was over. In Camden, New Jersey, Harold Vance heard the news on the radio in his living room while eating breakfast with his wife Eleanor and their 2 children, Margaret and Robert. There was no ceremony, no phone call from Washington, no telegram of congratulation from the Navy. The Sonobuoy program was still classified, and even if it hadn't been, Vance was a civilian contractor, not a soldier. He had never worn a uniform. He had never fired a weapon. He had never set foot on a combat ship. The following Monday, he returned to RCA's Camden plant and resumed his pre-war position as a senior radio technician on the commercial electronics assembly line. His wartime work was locked in filing cabinets marked secret. His name appeared in no public record, no newspaper article, no official history of the Battle of the Atlantic. The men who had flown the aircraft, dropped the buoys, and sunk the submarines received medals, promotions, and recognition. The man who had made it all possible went back to testing vacuum tubes. Commander William Parsons, the naval officer who had championed the Sonobuoy program and helped Vance bypass the Bureau of Ordnance, went on to far greater things. He served as the weaponeer aboard the Enola Gay, arming the atomic bomb that destroyed Hiroshima. He was promoted to Rear Admiral. His name appears in every major history of the Manhattan Project. He never publicly mentioned the Sonobuoy program or Harold Vance's role in it. Rear Admiral Wilson Caldwell, the man who had tried to kill the program in September 1942, retired from the Navy in 1946 with full honors. His official service record made no mention of his opposition to Sonobuoy development. In retirement, he wrote a memoir about naval ordnance that devoted 3 paragraphs to acoustic detection technology, without naming Vance or acknowledging his own attempts to block the program. Lieutenant James McAllister, the patrol pilot who had flown the critical demonstration over Norfolk in October 1942, the test that had saved the program, returned to civilian life and became a commercial airline pilot for Pan American Airways. He flew transatlantic routes for 20 years, crossing the same ocean where Sonobuoys had once tracked submarines beneath his wings. He told his children about the demonstration exactly once at a dinner party in 1958 and never mentioned it again. Vance himself rarely spoke about his wartime work. The classification restrictions remained in place throughout the late 1940s, and by the time the program was partially declassified, in the early 1950s, the world had moved on to new wars, new technologies, new heroes. Korea was raging. The Cold War was escalating. Nobody was interested in a story about a radio technician and a tin can from 1942. But Harold Vance's invention did not retire when he did. It evolved, and its legacy would prove far larger than anything he had imagined in that garage workshop. But the real legacy was not about medals or recognition. It was about what his $65 device became. In 1950, as the Cold War transformed the Atlantic from a battlefield into a surveillance zone, the United States Navy launched Project Jezebel, the most ambitious underwater acoustic detection program in history. Its foundation was the Sonobuoy. Not the crude CRT-1 that Vance had built, but direct descendants of it, improved, refined, and deployed on a scale that would have staggered even the most optimistic wartime planners. By 1954, the Navy had developed the SOSA system, the Sound Surveillance System, a network of permanent underwater hydrophone arrays installed across the Atlantic and Pacific Ocean floors. SOSUS was essentially Harold Vance's concept, made permanent. Instead of expendable buoys dropped from aircraft, SOSUS used fixed sensors connected by undersea cables to shore-based listening stations. The principle was identical. Listen to the ocean, hear the submarines, track them continuously. SOSUS could detect Soviet submarines from hundreds of miles away. During the Cuban Missile Crisis in 1962, the system tracked every Soviet submarine approaching Cuba, providing President Kennedy with real-time intelligence that proved critical to the crisis resolution. 4 Soviet Foxtrot-class submarines carrying nuclear torpedoes were detected, tracked and forced to surface by American naval forces, guided by acoustic detection data. The world came within hours of nuclear war, and underwater listening technology helped prevent it. Throughout the Cold War, expendable Sonobuoys continued to serve alongside the fixed SOSUS arrays. The technology improved dramatically. Detection ranges increased from 3 miles to over 50. Battery life extended from 6 hours to over 24. Signal processing evolved from a human operator listening through headphones to computerized systems that could automatically classify submarine types by their acoustic signatures. During the Vietnam War, the Navy deployed Sonobuoys in coastal waters to detect North Vietnamese supply boats. During the Falklands War, in 1982, British forces used Sonobuoys to track the Argentine submarine San Luis, preventing it from attacking the Royal Navy Task Force. During the Gulf War in 1991, coalition naval forces deployed Sonobuoy barriers across the Persian Gulf. Today, in 2024, every major navy in the world operates Sonobuoy systems. The United States alone deploys approximately 40,000 Sonobuoys per year during peacetime training and surveillance operations. The modern AN SSQ-53 DFAR Sonobuoy is a direct descendant of Vance's CRT-1 using the same fundamental principle, a hydrophone suspended from a floating transmitter, but with GPS positioning, digital signal processing, and detection capabilities that the wartime version could never have achieved. Over 30 nations manufacture or operate Sonobuoy systems. The global market for underwater acoustic detection technology exceeds $2 billion annually. And every single device in every navy, in every ocean on the planet, it traces its lineage back to a sketch drawn on a kitchen table in Camden, New Jersey in 1941. But the biggest lesson of this story is not about technology. It is about people. Harold Vance was not a genius. He was not a visionary leader or a decorated war hero. He was a radio technician who understood how sound traveled through water and who had the stubbornness to fight for an idea that everyone around him said was impossible. He did not invent sonar. He did not discover underwater acoustics. He took existing knowledge and applied it in a way that nobody with more credentials, more authority, or more experience had thought to try. That pattern repeats across every major military innovation in history. The tank was championed by Ernest Swinton, a war correspondent with no engineering background, who saw men dying in trenches and imagined a machine that could cross them. Our radar was pushed into operational use by Henry Tizard, a chemist who had to fight the British Air Ministry for 3 years before they agreed to build a detection network. The Norden bomb sight, the proximity fuse penicillin for battlefield wounds. Every one of these innovations faced the same obstacles. Institutional resistance, bureaucratic inertia, experts who knew enough to explain why something could not work, but not enough to imagine how it could. The lesson is not that institutions are stupid. Admiral Caldwell was not stupid. He was applying decades of experience to a problem that his experience had not prepared him for. The lesson is that expertise, when it becomes rigid, when it stops asking what if and starts insisting that's impossible, becomes the enemy of innovation. The people who change wars, who change industries, who change the world, are often the people with just enough knowledge to see the possibility and just enough naivety to ignore the impossibility. In every generation, in every organization, there is a Harold Vance sitting at a workbench somewhere holding an idea that the experts have dismissed. The question is whether someone like Commander Parsons will listen, whether someone like Dr. Bush will act, whether the system will bend enough to let the idea through before it is too late. And there is one final detail that almost nobody knows. In 1962, 17 years after the war ended, Harold Vance received a letter at his home in Camden. It came from the Office of Naval Research, forwarded through RCA's corporate headquarters. Inside was a single-page document, a summary of a classified study conducted by the Johns Hopkins University Applied Physics Laboratory, analyzing the effectiveness of acoustic detection in the Battle of the Atlantic. The study concluded that Sonobuoy-assisted detection had contributed to the destruction or neutralization of approximately 150 U-boats between 1942 and 1945. It estimated that the surveillance pressure created by Sonobuoy deployments had prevented an additional 600 to 800 successful attacks on Allied convoys by forcing submarines to evade rather than engage. Based on average cargo tonnage and crew sizes of the ships that were not sunk because U-boats were detected and driven away, the study calculated that Sonobuoy technology had saved approximately 30,000 to 40,000 Allied lives during the war. Sailors, soldiers, merchant marines, men who came home to their families because a $65 device heard the submarine that was hunting them. At the bottom of the document, someone had handwritten a note. No official letterhead, no signature, just 7 words in blue ink. "Thank you, Mr. Vance." We came home. Eleanor Vance found her husband sitting at the kitchen table that afternoon. The letter in one hand, his reading glasses in the other, tears running down his face. She had never seen him cry before. Not during the war. Not during the years of anonymity that followed not once. She asked him what was wrong. "Nothing is wrong," he said. Someone remembered. Harold Vance continued working at RCA until his retirement in 1968. He died in 1974, at the age of 70, in the same house in Camden, where he had sketched the first Sonobuoy on his kitchen table 33 years earlier. His obituary in the Camden Courier-Post was 4 lines long. It mentioned his years at RCA. It mentioned his wife and children. It did not mention the war. It did not mention submarines. It did not mention the Atlantic Ocean or the $65 device that had helped win the longest battle of the Second World War. But the ocean remembered. It remembers still. From a radio technician with an idea that admirals called insane to a weapon system that sank 150 enemy submarines, saved 30,000 lives, and changed naval warfare forever. Harold Vance proved that you do not need rank credentials or permission to change the world. You need one good idea, the courage to fight for it, and the stubbornness to keep going when everyone with authority tells you to stop. 150,000 Sonobuoys, 150 U-boats destroyed, 30,000 lives saved, $9 million spent. The cost of a single warship, buying a victory that 1,000 warships could not have achieved alone. If you know a story like this, a story about someone ordinary who did something extraordinary that history forgot, share it in the comments. The world is full of Harold Vances. Most of them never get their letter. Subscribe for more stories like this. Because the best history is not about the generals who gave the orders. It is about the people who built the things that made those orders matter. And the next time you hear someone say that's impossible, remember a radio technician in New Jersey who heard the same words, ignored them, and turned the ocean itself into a weapon. The generals didn't win the Atlantic. The admirals didn't win the Atlantic. A man with a soldering iron and a $65 idea won the Atlantic. And the sea, which had hidden submarines since the day they were invented, became the very thing that betrayed them. That is the power of one stubborn mind, refusing to accept what the experts said could not be done.